to identify patterns and trends in this material science data. Here you see this lots of institutes are involved, and in particular Aalto University here. You see the logo, apparently the stochastic logo, I've been told by people, that this can change, the punctuation is kind of random. It could be exclamation mark, or question mark, or double A. But anyway, so this is one motivation, so we want to automatically classify crystal structure in the normal archive. And we want to do it in a way that is robust with respect to defects, or and without using any user-defined threshold, because if you have 44 million calculations, there's no threshold that works for all of them. And the other one is the experimental motivation. So there are these data from atom probe tomography experiments that are very, very valuable. So this is a technique that is arguably the most important one, experimental technique to probe 3D structure. So you can visualize atoms in 3D. They can look at materials, I don't know, the iron, but also more complicated ones, and they give you elemental maps of where the atoms are actually in the material. So you see a small needle, and they evaporate these atoms. They hit a detector, and then they go back and reconstruct in some way where the atoms form. So these are complicated data, though, because for a data set you have hundreds of millions of data points. I think the record by the collaborator is I think 5.4 billion atoms in a sample. And so these are, of course, gigabytes of data. And the uncertainty of the position is very high. So we don't know exactly where the atoms are, because, of course, these guys are looking at individual atoms, so it's kind of amazing that they can do something with that. But there's an uncertainty in that, a big one. And at least 20% of the atoms are missing. For the best detector in the world, 20% of the atoms are missing, because they're not detected. So that's why we care about defective structure, because we want to have something automatically to go to this data and detect the structure. Detect nano-island could be VCC, FCC, nano-island, grain boundary. So that's the idea. And so here you see simple cubic, body center and face center cubic. And it depends on who you are, if you're a material scientist or not. They can be very similar, quite similar, that I don't really know for the pristine. But if you look, of course, the packing is different. So this is a simple cubic, and this is not really. Do you have another pointer? This is fading. Anyway, if you have one, just bring one. And so here you have a simple cubic, and then here you have a body center cubic, and this is a face center cubic. So the packing is different. And but it's still quite a challenge when you have lots of defects. So if you have a lot of random displacement, or up to 25% of the atoms are missing that, then it's a bit harder to tell which is which, right? And we want to do it in an automatic way, so that's our goal. And so we want a method that doesn't require any threshold, is robust with respect to defects. I mean, vacancies could be real vacancies in the material or not detected atoms. And random displacement could be due to thermal fluctuation or actually resolution, error in the resolution of the experiment. So error due to the low resolution of the experiment. And it should be very fast at prediction time, because we have gigabytes of data, easy to parallelize. And you saw that representing crystal structure is quite a tricky business. They are like complex 3D structures. And there's lots of symmetries that you want to build in, because you need to encode that, because we know by physics that these things should be invariant by symmetries, and we don't want the machine learning algorithm to learn that, because it will need much more data, and data are costly and hard to get. And also you need bigger models if you don't have invariance. Okay. So, great. Okay. And so now, and you saw a very successful descriptor proposed by, for example, solved by Gabor Ksani. And can I also change the slide now, right? So, can I have the other one to change the slide? It's changing that. Okay, so it's the substitution. Okay, sorry about this. And so we have, and then our Wheeler that proposed neural network and symmetry function for that, and Roop and others for noise cancellations, for example. And so, but these are all real space based, and they look at atomic neighborhoods, which is the right thing to do for what they're doing. They're an incredible success, as you saw, for potential energy surfaces and lots of things. But we need to classify crystals, so they taught me that in solid state that the reciprocal space, that's what you should look at if you are classifying crystal structures. So that's what we do. And so the idea is, okay, thank you. So the idea is that we have we go in reciprocal space, simply calculating the diffraction pattern. So here you can see the math. It is very simple. You can calculate the amplitude of a plane wave that originates from the scattering given by the atoms that are at some position in the material. So here you see you get different phases. You sum them. This is a Fourier transform, and here you have some factor that depends on the type of atom. And then what we do, we get this 3D field, and then we project on the planes that are perpendicular to the wave vector. So that's the idea. And so this is the intuition. So our structure are defined by lattice vectors and atomic position. So we have the freedom to rotate these structures. And how to represent actually this structure in a quite unique way is that we have a structure to classify, and then we rotate around the crystal axis that we have, and we rotate around 45 by 45 degrees, let's say around the x-axis, and then we represent the diffraction pattern on this image as a red channel, and then around the other axis on green and blue. There's no particular reason to do RGB, but you know that's what images are, and your TV is like that. So I thought it was a nice idea to put them together in an RGB image. And that's how we represent these complicated structures, just simply RGB images. And so the diffraction fingerprint is has some nice property, which is size invariant with respect to your unit cell. Because you know that the diffraction points will be in the same position no matter how big the supercell is. And here you can see that. And what changes is just the width of the peaks, because that's due to the indetermination principle. But you see, like already, well, like, I don't know, this is probably 64 atoms. It's already very similar to the very big supercell. It's opposed to the perturbation of the structures. So here you see this pristine structure, and this is a structure with, I think, either displacement or at least 25% of the atoms are missing. I think this is with vacancies. And you see same diffraction pattern. And so this is nice, and it has the same dimension regardless of the atoms that are included in the unit cell. This is interpretable because we are looking at them, they are images. And it also, here I calculated with different, for this prototype I showed you before. And the diffraction fingerprints are different for all classes apart from the rhomboidal and hexagonal. They have the same diffraction fingerprints. But these structures are very similar in the real space, so we are okay with that. And so here we go. So this could look the same, but actually there's a small difference. Can you spot the difference between this and that? It's hard on the projector. But this is green and this is yellow, right? And this is I know it's hard to tell, right? But in your network can tell, and that's why also these RGB, because we want to distinguish these two structures. So anyway, so now we are here and we represent a structure as an image, and then you know where I'm going. We want to use neural network to classify that, and we will use convolutional neural network as was introduced briefly before. But before I do so, let me just get to the ground and just explain very briefly what a neural network is. And so it's nothing fancy really. It's if you have a standard n-layer neural network, just applies to the input data a series of linear and nonlinear transformations, one after the other. There's no magic. So here you have your input data, and then you have A, that's a transformation, and this is an affine transformation. So you get here, these are the weights, and these are the biases. And these are going to be the parameter of your network. And then you have a nonlinear operator that is applied to this. And this gives the richness of the network. And the different nonlinear operators, I don't know if you're familiar with them, but these are ReLU, sigmoids, and you just apply very simple nonlinear transformation. So ReLU is like this, it's 0, and then it's just a straight line, or a sigmoid is like this, tan H. And there are different types of nonlinearities you can put in. And it's quite remarkable that such a simple thing can learn so many things in real life. So you have computer vision, various use success by neural network, speech recognition, machine translation, your Google Translate, and in particular for image recognition, convolutional neural networks are state of the art. I mean, they perform incredibly well, and were proposed in 1989 by Jan LeCun. And actually, by the mid-1990s, they were reading 10% of the checks of the United States. So like, you know, it's quite remarkable that we like apply to technology very, very quickly. And so that's now let's just give an intuition about CompNet. Maybe you already know CompNet, so sorry if I give you this introduction, but I think it's nice to have an intuition about how they work. So here you see a picture of 3 dogs, right? And here you see what the computer sees, so just numbers. Now, just think about how do we humans subconsciously classify an image. Have you ever thought about that? No, right? Yeah. Neither have I before giving this talk, so but actually I look it up, and actually it's true. I recognize myself in this. So you look for identifiable pre-learned features. So here you see that these are the paws, the tongue out, and then you know your little ears. These are dogs. We know from our experience. So we essentially look for pre-learned features, and with our experience, we associate these pre-learned features with something that we know, and we associate it to it. I want to do the same with the computer. But the computer, every time we run an algorithm, it's just born, right? I mean, there's no experience, right? The initialization are random numbers, so the computer doesn't know anything. So what we do the same though. And so you want to build a hierarchical representation of the data, starting from low-level features, like edges and curves. You want to detect them, and then stuck in layers, you will build more abstract concepts through a series of convolutional layers. So that's why you need deep learning. Because the first layers will learn low-level features, and then you combine them in a hierarchical fashion, in an automatic way, driven by the data. So then that actually we will show this. This is really true, and we will show this for the case of our material science neural network. And so the intuition is very, very simple. So you have this, let's say you have this image, and you want to detect when there's a curve in the image. So this is how you see a curve. I mean, this curve, and here is how the computer sees it, so non-zero elements here and zeros in other locations. And what you do is a convolutional layer, so you slide this, let's say this filter on the image. And at each position, you multiply the matrices, you know, element-wise, so you multiply this 0 times this 0 and so on. And then you sum up the result. So you see that here you have non-zero elements in the image, at the same location as they have the same shape as the filter here. So you get a very high number. So essentially you have a high value because the shape, so the mouse, resembles the filter. And conversely, if the filter doesn't resemble the image, then you get a 0 because you multiply non-zero elements with 0 elements and vice versa. So the output of a convolutional layer is simply a 2D activation mouse, a 2D activation map that gives the response of that filter to its spatial position in the image. That's all. And then, of course, in practice, it's you have more filters because you want to learn different type of, let's say, edges or curves or so on. So you need multiple filters and multiple layers. But that's it. And 2 things to remember that will come towards the end of the talk. The first is that the complexity of the filters increases layer by layer, and that the filters are minimized. Are learned minimizing the training error, so directly from the data. So, and just to give you a quick flavor of this is a neural network that I train to classify cubic structures, but the most general one with non-cubic structure is similar. And we have 6 convolutional layers, and these are, you know, you have max pooling layer and the fully connected one for the experts in the room. But and then filters are 32, 16, and they go down to. And okay, so this is the network, and now we want to train this network to do science with it. And so the idea is we need a data set, and in particular we need a training data set. So what I did, I took the AffloLib elemental solid data set from that was generated by Stefano Curtarolo, and it is in the Nomad archive. So I read this from the Nomad archive, and this includes 90 chemical elements, and you have supercell of various sizes. And you have roughly 10,000 structures, and these belong to the 7 classes I showed you before. And you divide in 90% in training and 10% of validation randomly. And the neural network is quite small, so I can train on my laptop. And the prediction takes 70 milliseconds per image. And so we see that we can obtain 100% training and validation accuracy, so we can learn this image very well with a small neural network. And also the validation accuracy is 100%. Now, this is great, but it's not the end of the story, because we want to test on defective data set. That's what we are after, right? Because we also need to remember that when we do this random split between training and validation, our data are really structured, so we need to be careful in evaluating, because it's easy to overfit without knowing it. But here, so this is how we train the neural network, and now the real test is on defective structures. So I make a defective data set, starting for the pristine one, and adding defects. It could be random displacements at 0.08 angstrom, and removing up to 25% of the atoms, and substituting them. And then here you have roughly 140,000 images, and then I use the neural network training before to predict. And then we obtain 100% test accuracy. So that means that we really can generalize to unseen data in very defective structure that were never included in the training. So that's very nice, so happy with that. And now we want to explore our model. So to do that, we have, let's say you have a body-centered cubic here and a simple cubic. Now you can see from this image that if you remove this central atom here, all of them, then you get simple cubic. So it's very simple to realize. Now you can remove some of them, and not all of them. The neural network only knows about the BCC and on the simple cubic. And so we want to see the neural network, since the representation is continuous and the neural network is able to interpolate. We do that, and we see that here you have the central atoms being removed. 0% of central atom is removed is BCC, and 100% is simple cubic. This is only where we train on really like these parts. So here you get the classification probability by the network, and the neural network here you see is purple, so it's very sure that this is BCC, and then up to, I don't know, 60, 70%, and then the neural network starts being unsure, and then you have a crossover as you would expect. And then the neural network thinks this is now a defective simple cubic, and now it's very sure about it. It's not 50%, life is non-linear, so you should not expect that. And another model exploration, a bit more involved. So you can, I took from the AfloLib website, you can generate prototypes. That's a very nice tool to do that. And you can start with a rhombohedral prototype, and then changing the value of Q, which is essentially related with the lattice vectors angles. You can have body-centered cubic, simple cubic, and face-centered cubic. So this is a probe. Now we will vary this Q and see if we can actually, because when this value is that, then the rhombohedral will be a simple cubic. So we want to detect if the neural network is able to do that. And indeed, we can do that. So we have order parameter here. I'm sorry, this should be Q. And you have a classification probability. Here you start with BCC here, and then see it becomes yellow, so that's rhombohedral, and then exactly at 90 degrees it gets simple cubic, and then here the same for simple cubic, and then face here. That's nice. And but now there's a question of in any machine learning talk applied to the physical sciences, or actually in general natural sciences, we want really to know if we got the right result for the right reason. And that's why we do science to start with. And so we try to do our best to open the black box of deep learning and these algorithms that apply to our data. So and this we'll try to do it in two substeps. The first is very general, and so I try to convince you that why deep learning is better than shallow learning. And this is not my work, but there are some papers that were recently published on the archive by some people at MIT, and they just want to present something related to that. And then we will go back to my research, and we will show that how does our convolutional neural network actually arrive at this classification decision. So this is deep learning because you have more layers. That's simply simple as that. You have 4 hidden layers. And here this is shallow learning because you just have 1 hidden layer. So that's terminology. And how do you know? Okay, to answer the question how good neural networks are, you have 3. Remember, you have always to take into consideration these 3 things. And this comes from this very nice paper that I encourage you to read from 2017 by some people at MIT. So there are expressibility. What class of function can the neural network express? Now, that's only one thing. The other thing is efficiency. How many resources do you need? If you need infinite amount of data, then it's useless, right? You don't have that. And learnability. So how rapidly can you learn this parameter? Remember, all the neural network trained on gradient descent, so it's very simple. So it's not that you can learn this parameter. This is a field of active research, so we don't have an answer to that. But the expressibility was really known, and I think it was actually quoted before by Baylor, something related to that, that a neural network with a single hidden layer can approximate any smooth function to any desired accuracy. So you just need one layer, right? But then why you heard about deep learning and not shallow learning, right? Because if you just need one layer, and so the answer is inefficiency. Because so if you have a deep network here, let's say 3 layers and 12 hidden neurons, and then you flatten that, and you get a shallow network, let's say with 12 hidden neurons and 1 layer. How does it cost you to flatten? Is that a good thing? Is that a bad thing? So so how many neurons we need in the shallow network to maintain the same expressive power as the deep network? That will tell us if we really need to do deep learning. And so they showed here that you have an exponential cost of flattening. So if you want to, you can write down a simple neural network to multiply variables. And it turns out that you need exponentially many neurons in the shallow network with respect to the deep network. That's quite amazing. This is a theorem. You can just look it up. And if you need to multiply 32 numbers, exactly, you need 4 billion neurons. Or in the shallow network, or 32 in the deep network. And this is kind of reminiscence also if you know the discrete Fourier transform when you do these factorizations. That's like similar idea. And this also is valid for polynomial representation of degrees d. You need at most d neurons for the shallow network and logarithm of 2, logarithm of base 2 of d neurons at the most for the deep network. Okay. Okay. So then you have 10 minutes. Okay, so it's 35 then in total. Okay. Okay. Okay, then you have okay, so this is an example. So what we do, so to look and to understand how we arrive at the classification decision of our network. So I told you that we have convolutional layers here. We stop one after the other and we arrive at the classification decision. What we want to do is look at what are the most important part of the image where the neural network looks to arrive at the classification decision. And so you need to invert this process and look at what are the most important part. And to do that, you simply apply the convolution and unpooling. So you go back in image space. And this was proposed in 2014 in the machine learning community. It is a very famous paper. And we team up with Devinder Kumar at the University of Waterloo to apply a variation of this technique that he developed on our data set. So what we are looking at is attentive response maps. So we are looking at, you have an image here, and you are human, you see that to classify this image, as you saw before, you look at the relative orientation of the points, so the relative position of the points here. You will not look at the shape, but where these points are arranged. And the first layer in the neural network look just at the shape around here, and that's not the right thing to do, and still. But the third layer, the neural network starts learning that it should look at relative positions, and that's good, right? Hierarchical representation of the features. And here you see, here you're looking at 6 points. So that's actually a demonstration of this hierarchical representation of features that is building automatically to the data. You can do the same if putting the RGB, so the 3 colors, and you see even more clearly. And you arrive at the last layer, and if you sum up these attentive response maps, which means where the neural network looks to arrive at this classification decision, that's what the neural network knows about the data, that's where it looks at. And you get a beautiful template that is learned directly from the data. So it's really looking at the right points. And so this is, and here you have a little animation, you can see that the neural net going through the layers, so different attentive response map of the layers, you get increasing layer of abstraction. But now I told you that we want to tackle heavy diffective structure and also polycrystalline structure. So we want to tackle hundreds of thousands of atoms with grain boundaries, and they have I don't know, they are random orientation between them, and you have heavy defective structure. Say 40% of the atoms are missing. And we want still to to detect what's the most similar prototype. And here you don't have a label for the whole structure, but you have local labels in a way. Because before you have like a simple crystal, but here you have a boundary. So how do we get by? How do we tackle this? We bring forward two ideas. And the first is how to represent a material. So it's similar to what I showed you before, but now yet a bit different. So we have a three-dimensional diffraction fingerprint we bring forward, and we isotropically scale the structures according to the nearest neighbor distance. We calculate the three-dimensional diffraction pattern, and now instead of projecting, we construct a rotational invariant descriptor based on spherical harmonic function. In particular, I want to focus on this part. So you have a cube, right? You have a diffraction, and this is a scalar field. So what you can do, you can get shells, like concentric shells, and then for each shell, it's a sphere, so you represent in spherical harmonics here. And then for each L, you can sum the between minus L and L of these coefficient squares. This is pi L of G, where G is the intensity here. And you do this for all L, and you get a rotational invariant representation for this shell. Now you do it for all shells, right? So here, and you get a rotation invariant representation based on the diffraction fingerprint. Here, this was actually known by the applied mathematical community. This is similar to SOAP in a way. I mean, not the details, of course. And then this is how I calculated them. This is how they look like for the three classes. And here you see that they are different across these three classes. I just did the cubic for now. And still very stable with respect to defects, 40% of vacancies. And it's still the same. And this is now invariant with respect to translation, rotation, atom permutations, isotropic scaling. And it's robust, and still we have the same dimension regardless of the atomic structure, and it's compact. So only few elements are non-zero. The dark blue here is zero. And so now we have an image, and we want to, again, we will use the convolutional neural net. And to build the database, I just take the AFLOLib, and I generated these prototypes that are, and I just take these three classes, 90 chemical elements, and I put 5 random rotations. We don't have to, we can just take one, but this is just for numerical purposes. We don't need to data augment because this is a rotational invariant by construction. And now you have 1,000 images, and I train the neural net on them. The neural net is really tiny. It takes, I don't know, a few minutes on my laptop to train. And we get 100% accuracy, training and validation. And but now we want to apply this neural network to the polycrystalline structure. So how do we do that? Because there's no label for the whole thing. So we propose something called strided pattern, something we call strided pattern matching. So you have this defective structure, and you get the box, and you slide the box throughout the material. At each position of this box, you extract the atomic positions, you calculate the diffraction fingerprint. And then you have a neural network that was trained on the prototypes from before, and you just apply that, and you get the classification, the probability of classification. You don't retrain on that, and you don't need to worry about, you can use different size of the box, because I showed you that invariant with respect to this supercell size or the rotation, and so on. So that's what we do. And now you have here you have a pristine polycrystalline structure. You have a grain boundary here. This is roughly 2,000 atoms. But actually, last week we did 37,000 atoms, and kind of more phases in that. You can do that too. And here you have diamond and FCC. So you want the neural network to recognize this. And here you have a grain boundary. This is generated by a computer. Just it's not relaxed by EFD or anything. That's not the goal. But now we apply this technique, and we obtain the classification probability for being diamond, because I told you the neural network outputs the probability. So here you get 1. So the neural network is really sure this is diamond, and this is 0. So the neural network is really sure this is not diamond, and that's what you would like to see, right? And I want to stress the fact that the neural network is not trained on this data; it's trained on the prototypes from before, that in principle have nothing to do. I mean, of course, they have the same physics there, but this is just to show that the neural network trained on the prototypes is really generalizing well. And here you do the same for the classification probability as phase center cubic, and here you get 0, so this is diamond, it's not FCC, and then you're very sure that it is FCC. And interestingly is that here on the boundary, you have the neural net is unsure, and that's actually right, because which kind of structure is that? It's an intermediate one. There's no FCC, no diamond. So that's nice, you can also detect range boundaries in this way. But I promise you that I wanted to have a defective structure, so I just took this and removed 40% of the atom, which is quite a lot. And again, use the neural net to have a strain of the pristine structure from before. And you still have very good classification. So here you get the classification for the diamond, 1 and then 0 FCC. Here it's a bit darker, but it's still 0.7%, 70% sure that this is diamond. So still classifying correctly. And the same thing here. It's a bit more noisy, but also this data might be that this is more similar to FCC, for example. And so this is so that we are happy because we can construct that. Of course, this is not the end of the story, because the data from the experiment have actually they have distortions, and like the displacement that they have is much greater than 0.1 angstrom that we're tackling here. But this is where we are heading. Now we are trying to have a student is trying to tackle this challenge with experimental data. So this brings me towards the conclusion. So I introduced the challenge that we have classifying the prototypes. This kind of structure according to the prototype with heavily defective structure. The two representations that we bring forward that are tailor-made for the task of crystal structure recognition. So two-dimensional diffraction fingerprint and three-dimensional. I showed you what are the neural networks and the CompNet that we use, and this slide pattern matching technique, and an application to FCC and diamond for the crystal structure. And also we try to open the black box and see why the neural networks arrive at the classification. And this brings me to the most important slide of my talk, the people that made this work possible. So Matthias Schäffler, the director of the Fritz Haber Institute, Luca Zinghelli, another group leader of the Fritz Haber Institute, Andrea Leiter, a very talented PhD student of mine, Devinder Kumar at the University of Waterloo, he's doing his PhD in computer vision. And then we have NOMAD, the European Union, Max Planck for founding, and you for your kind attention. Thank you very much.
Thank you very much for this great overview of your ongoing work. Angelo's question to you.
Yeah, okay, nice presentation. But I was a little bit confused. You are confusing with the neural network and deep learning convolution neural network. So you are saying neural network. It can be marked here. That is neural network. But the deep learning is CNN is convolution and neural network. So this is applied the blocks algorithm, just simple as. And also, when it comes to the black box, again, black box, if you fail for the prediction, then it tells you why your black box is failing. That actually, this is the first paper is published by Marco from the University of Washington. This is library, the paper name, Why Should I Trust You? So this is the paper title. And the library based on that paper is called the line. And that actually has the two principles, the model interpretability and the model transparency. So, the black box can actually, this line or whatever, this why should I trust you algorithm tells you when you have failed the prediction. So I wonder in this particular cases, because they have examined one cases from the feature engineering, because they want to predict the foxes actually, and they found like your case is 100% accurate, and they wonder why it's so 100% accurate. But what is tell about actually this deep learning capture the image of the background. There are always snow in the background. And then if it's snow in the background, then it tells, okay, this is the white fox. So I wonder, particularly in your cases, you got 100% accurate. So it could be the misleading somehow.
No, exactly. That's the whole point of showing.
Misleading. And you have to use exactly the same model. And you have only 7 classes. And it's not really.
Okay, so this is the motive. That's why this we are looking at. It's called attentive response.
But you have to find out why you have the problem, and then black box will tell you this is the problem.
No, I mean that's not true because you can. There are multiple neural networks, and you should actually look at the neural network that is looking at the right spots. And here, it's not that you need to get a wrong example to see if the neural network is learning correctly. That's not true because here you can look. These are called attentive response maps. So you look at the last layer of the neural network, the convolutional filters, and you look what are the most important ones for the classification decision of the convolutional neural network. What you're talking about is the sensitivity analysis, which is very different than this. Because then the sensitivity analysis, you need negative examples to see why you're wrong. And then here instead, you backpropagate. So this is what is, this is Ziller is like very famous. It's a 2,000, 3,000 citation. And this was a student of Yannick Kuhn and Hinton. They are the director of Facebook research and the godfather of deep learning. And that's built on top of this. This is there was co-work. It was work by a supervisor of David together with Ziller. So that's we are working that, and that's different than sensitivity analysis. It's very different work.
Great. Another question.
Yeah, so it's really beautiful work. Thank you. I think this diffraction fingerprint is a great idea for the DFT data. I'm a little less sure about the atom probe data because you mentioned at the very end that accuracy of the atom probe position is, fraction of an angstrom, something like this. So if you just took a FCC box and you just placed atoms randomly by 0.1 angstroms, does the diffraction pattern look anything like FCC?
Yes. I mean, we displace up to 0.08 angstrom, and we arrive at an accuracy 99.91%. Then if you have, let's say, when you get around 1 angstrom displacement, it depends, of course, on your lattice. It depends. Like 1 angstrom is related with the lattice displacement. But we show that up to 10% of the lattice displacement, so you get a lattice vector, then it's still stable, and then you get really a drop in the accuracy, because then you get, as you say, the diffraction pattern, you really don't have a crystal anymore. Because actually the definition of the crystal is that a well-defined diffraction pattern, because then you have quasi-crystal, and that's actually, so then that's the kind of, atom probe data. Is that really a crystal when you see, because that's a lot of error in the experiment. So there are two things. One is really a crystal, and then we try to classify. Another thing is that there are error in the resolution that are much higher. And if you look at it, it should be amorphous, because if you look at some atom tomography data, they look amorphous. So to go and classify this data, we need more work. But to get your question, up to 10% of the lattice, we are able to classify very.
It's a really fascinating point, like up to which size is a crystal actually a crystal anymore? If you have a nanocrystalline sample, right? Is it starting to get amorphous? So that's a great point.
Yeah, so what do you think about protein crystals? Because hydrogens do not really show up on diffraction maps.
Well, actually here these are calculated diffraction maps. So our starting point is 3D structures. So here, actually, I use, you have this factor, the atom form factor, for Xa, for example, and that's very low for hydrogen, but I know what the atoms are. So I actually increment by 2 the weight of the atom, so let's say instead of using if I have hydrogen, I represent this as, lithium, for example. So because here we don't start from X-ray. So, but the problem that I could see in that is that then it starts to be a very complicated diffraction pattern, and then there's maybe not what you use here, but I'm not sure. One drawback of this is that the diffraction pattern is centrosymmetric by construction. like to a very good approximation. So y of minus x minus y minus z is the same as x, y, z. So you cannot distinguish all the space group. You cannot have piezoelectric effects and so on. So, but for the crystals, I think.
That's a question.
So there are existing methods for doing this phase detection in polycrystalline materials that are based on a simpler method, just basically analyzing the local coordination. So have you benchmarked against some existing methods?
We didn't benchmark on this. We will. I don't know how the. Yeah, it's a good question. We benchmark against, of course, SPGV, for example, a fine thing to get this right space group for the pristine one. And then if you remove one atom, then they get P1, right? So that's the benchmark we did. And but yeah, that's an interesting benchmark. I'm not sure because they are all based in real space, I suppose. So here is really what saves you is that you can get rid of lots of the noise because you're going in reciprocal space. But it's something that we should look at.
I don't see any more urgent questions, so let's thank our speaker again, not just for a nice talk, but also for a really nice discussion. So.